Welcome everybody to this panel on digital twins for cyber physical production systems. My name is Christina Hattas. I am a policy officer at the German Informatics Society, and our team is supporting IFIP in the organization of this panel and event series. IFIP, the International Federation for Information Processing, is turning 60 this year, and to celebrate, we have organized a series of panels all dealing with the topic of the future of information processing. We will be recording the session today, so you will be able to access it later on the IFIP YouTube channel, and you can find more information on the IFIP Jubilee webpage, which is available at ifip.org/jubilee60. Now, without much further ado, I would like to hand over to our guest and organizer, Achim Rettberg and Graziano Pravadelli. Please enjoy this panel discussion.
Systems. We have the right panelists, I think, to talk about it. We have two moderators, that's Graziano and myself, and we have three panelists, and they will also give a short statement about about this topic. So let me introduce briefly the first, the other moderator, Graziano Pravadelli. He's professor at University of Verona, also an expert in embedded system design, modeling, verification. He's involved in the major conferences in this area like DAC and FD and FDL, and also some others. Yeah, this is his main research, only to give a brief introduction. So then I will hand over also to Graziano, and you can proceed further.
Thanks, Achim, and welcome everybody to this interesting seminar today. I'd like to introduce Achim as well. He is a professor for human-machine interface technologies at the University of Applied Science, Hamm, and he is also an extraordinary professor at the Karl von Enschede University of Oldenburg. He is the chair of the TC10 Computer System Technology of IFIP, and also the chair of the IFIP 10.2 Working Group on Embedded System. And he has a lot of publication in very relevant topic related to real-time system, hardware, software architecture. So, Achim.
Thank you so much, Graziano. So then let us introduce quickly the panelists, and we will proceed to first start with Samadhi Chakraborty. I always don't know if I spell your last name right. He's a professor of University of North Carolina in Chapel Hill. Was previously briefly for some years, he was at Technical University of Munich, yeah? And he's also involved in all the major conferences in cyber physical embedded systems area. And his main focus is also in the cyber physical system, one of the heroes, I would say, in this kind of area, and you can enjoy later what he will give as a statement about that. So then, Graziano, I will hand over to you again to introduce some other. Graziano,
okay, yeah. Yes, of course. Another speaker today is Archimedes Canedo. He is currently the principal key expert scientist with Siemens Corporate Technology at Princeton, where he leads a team of 150 scientists and engineers in the area of automation and control. His main research interests include cyber physical system, design automation, programming languages, compilers, etc. And in these fields, he published more than 50 papers, and he also got several patents.
Okay, and then last but not least, Franco Fumi, professor also from University of Verona. Franco is also, I think, great expert in this embedded system design, also in computer architecture. He's involved in RTL to software, how to build that up, transaction level modeling. He was as far as I remember right, he was the past chair of DATE 2020 or 21, and no, sorry, at this time you were chair. Next year will be past chair. Sorry for that. And so, yeah, he's an expert also in this area of embedded and cyber physical systems. And now I will hand over to Samarjit to start with his first statement about what is cyber physical systems. Come on.
Thank you, Achim. So let me share my slides. Right. Yeah, so good afternoon and good morning to all of you who are attending this panel. And my name is Samarjit Chakraborty. I'm a professor at the University of North Carolina at Chapel Hill. So I will, in this brief presentation, essentially talk about three problems or three challenges. I will not give much of a solution. And the first problem that I'm going to talk about is that in modeling. The second problem would be in the area of timing analysis, and the third problem is in the area of algorithmics. And this statement essentially comes from someone from academia, and I'm sure you will hear other perspectives from people coming from the industry. And Franco finally, I believe, is going to try to bridge this gap between academia and industry. So I will not go into the details of what is a production system. So I guess all of you have some picture in mind when we talk about a complex production system. And of course, in such a system, there are the machines that actually do the production. Then today, there is a complex IT platform or an embedded systems infrastructure that drives those machines. And finally, we have the product specifications. And these are the items that are essentially processed. Now, as you might imagine that all of these individual players in such a production system have completely different life cycles. So the amount of innovation today in the IT infrastructure domain is probably much higher than in the mechanical engineering domain. And as a result, it could be that there is a IT platform or a CPU upgrade, or maybe an operating system upgrade, or an old camera is replaced by a new camera. And the moment something like this happens, this tight coordination between these three players essentially breaks down. And this might, a small change in this IT infrastructure might trigger a much bigger change in the control algorithms that are driving the machines. So for example, a small change in the product specifications might require a completely different machine. A change in the camera resolution might completely disrupt the accuracy of the whole system. And one of the main challenges that this production domain faces is that given these different innovation cycle times in these different domains, how do you cope up with these non-aligned changes and not have to change your machinery completely the moment a small camera in the system changes? Now, in the industrial automation or production domain, there are level 2, level 3 automation techniques that are defined that enable this coordination between different units of the production line. But as this entire system becomes more complex, not just from the IT side, but also from the machinery side, one of the main questions that the industry and also the academic research community is facing is, how do you handle these types of changes that I mentioned in a purely automated manner? Now, this is what brings us to the concept of cyber physical production systems, where the picture is that we have a number of now interconnected but intelligent systems that are capable of automated adaptation. And what I would like to argue about is that in order for this vision to work, you need accurate models. We need accurate timing analysis techniques, and we also need algorithmic techniques that currently today do not exist. So coming to the first problem, of course, I don't think I need a big motivation to explain that for such a system to work, the underlying core of many of these systems are feedback control loops, and where you have a plant, which in our case is now a machine that has to be controlled in order to achieve a certain production goal. Now, I guess all of you in the audience know that, such a plant is the physical system. And on the other hand, we have the controller, which is a software entity that is running on the IT platform. And first, the obvious disconnect between the two is that the plant works in continuous time and the controller works in discrete time. And how do you reconcile this difference between a continuous time evolving plant with a discrete time evolving control? Now, typically, we use standard control theory, and there are lots of associated tools, common among being MATLAB and Simulink, that you use to design your controllers. But whenever this controller is designed, it is often the case that for the control theorists, there is little view on the complex IT platform that exists today. And as a result, there are the embedded systems engineers and the software engineers who design the IT platform, and they do this design process independently. And finally, in the last stage, when the controllers are integrated with these IT platforms, a lot of assumptions, or rather the idealistic assumptions that were made about the IT platforms by the control theorists do not hold true. For example, during the controller design phase, one might have assumed ideal timing behavior, but however, in practice, especially for complex IT systems, those timing behaviors are far from ideal. And we see this discrepancy between the controller design expectation versus the performance that we see in reality. And again, therefore, this is a problem because of the modeling gap between the models that were used when designing the physical systems and the controllers and the actual models that exist in reality.
Samarjit, sorry to interrupt you. I believe we're only seeing your first slide and not in full screen. So probably the share is not updated.
No, Aki. For me, it's working. Everything.
You're seeing it? Really?
Interesting. I see everything. I see.
Okay.
When yes.
Okay. Because I would not know what else to do.
Okay. Okay. Sorry, but I only see the first one. But that's fine. If you guys see it, then let's carry on.
Okay. Right. So the one of the ways to cope with this modeling gap is that one could have a partially specified controller and a partially specified IT platform and do some sort of a co-synthesis. But in order to do that, we need detailed timing information of the IT platform. And I'm going to illustrate to you why is that a big challenge today. So in almost any automated and especially intelligent production system today, there is the following setup: that we have a camera, and the camera is essentially detecting what is the state of the system. And based on the state of the system, you take a control action. Now, of course, this camera image has to be processed through some image processing pipeline. And today, this image processing pipeline almost invariably contains some machine learning techniques. And because of their computational complexity, they cannot be processed in real time purely in software. And as a result, you have a lot of hardware accelerators like FPGAs, GPUs, etc. So once this processing pipeline is over, then there is a decision that is taken, and then this decision is applied to the machine, which then goes ahead. And so this could be, for example, some sort of a robot arm that is picking up something, or a machine doing something. But this robot arm action or the machine action depends on what the robot sees about the environment through a particular camera. So the correctness of this entire system is not just the functional correctness, that is the robot arm moves in a particular manner, but also the fact that it moves at the right time. Now, because of this complex processing in this hardware platform, what we would have is we would have a scenario like this. And on this slide, I have a simple video, which is essentially a surrogate of the kind of scenario that I'm describing. So here, what you can see at the bottom right is a small metallic sphere. And the goal is that this metallic sphere has to be suspended in air by correcting the magnetic field. And the position of this sphere is always captured using a camera. So if I play this video, you will see that there is an Ethernet camera which processes frames at a very high frame rate of 178 frames per second. And this cannot be done at this rate using purely software. So you have a large array of complex hardware accelerators. So the main question is that before you take the control action or design your controller, you would like to know what is this end-to-end delay between the time a frame is captured and the time at which a control decision is taken. And the system has estimated the accurate position of this levitating ball. So the processing in this case, which is although a relatively simple platform, is just a system on chip platform where you have a processing element and an FPGA. And the main issue is that the data comes over this Ethernet port, and then this data has to be routed through multiple interconnects to the programmable logic, which is this FPGA fabric. And in this FPGA fabric, there are multiple algorithms. For example, in our case, there is a Gaussian noise eliminator, there is a candy edge detector, and so on. And after this processing is done, the data again goes back to the SoC. And in this SoC, there are the remaining processing steps that are executed. And finally, the actuation output is sent back again through this port to the electromagnet. Now, the issue is that how do we estimate the accurate timing from the time Ethernet frame enters to the time the output is reached here and this output goes into the controller. Now, if you take a closer look at the system, you will see that there are really many things that are going on, but more importantly, you can see that even this relatively simple control task actually involves many tasks that are spread out across this heterogeneous system. And there are many hard to predict components as a result of this transition between the system on chip platform and the FPGA. Now, we have done some work as to how to resolve this. There are, of course, design tools in FPGA design that are available to trace all these details that are happening. But one of the main problems is that this tracing really happens at a very low level of abstraction. And as a result, there is a lot of data that is generated, and you cannot monitor such a system for more than a couple of seconds. But the main issue is that you might be interested in a much higher level of abstraction, right? You might be interested in only certain events. And there currently does not exist any tracing method where you could define those events and just monitor those particular events of interest, and as a result, monitor the system for a long enough time. And of course, it is needless to mention that you cannot analytically or mathematically model all of this and do accurate timing analysis. And one of the techniques that we have come up with is we put in a trace core here, which is a very small part of this FPGA fabric, where you can define the level of abstraction at which you need to monitor things, and you could monitor only those particular events at a very high level of accuracy that you can see on the right-hand side. So you could really get detailed timing information of particular events that are of interest, and then use this information to get timing data that can be used to run your control algorithm. So the last part I would like to talk about very briefly. So I talked about the modeling issues that exist today that have to be overcome in order to realize this cyber physical systems production challenge. Then I briefly talked about the timing challenge. And then finally, I would like to talk about some algorithmic challenge. And again, all of us are quite familiar with this area of scheduling. You know, I myself come from a real-time systems background. But however, in the cyber physical production systems domain, a very simple problem is that you have multiple machines and you have a job that needs to be processed via these multiple machines. And a simple scheduling question that could be asked is, what is the sequence in which this job needs to be processed? Because the different machines have very different characteristics. Some machine might have a much harder drill bit, but it might and run much faster, but it might consume a lot more energy, whereas the other machine might have other characteristics. So given requirements on processing time, energy, machine wear and tear, what is this optimal choice? Now, you could think of it as a simple machine scheduling problem, but one of the main issues is that the processing at each machine is not defined by simple execution time properties as is commonly studied in academia, but this processing is modeled using a set of differential equations, because those differential equations accurately capture the continuous time and the continuous process in which a material is essentially processed. And as a result, we have the following scenario. We have M1 to Mn at the different machines. So this is at, let's say, the stage 1, again, the same machines at stage 2, again, the same machines at stage 3. And all that we need to do is we need to start at a particular machine, say M1, and at the next stage, decide what is the next machine. At the next stage, decide what is the next machine. and so on and so forth until we have the finished product. The main issue here is that the processing now in each of these machines is defined not just by execution time parameters, but by a set of differential equations. So given this space of different differential equations controlling the different machines, the problem is how do you determine each of these mode transitions such that you reach the final state, which is the desired state of the product, and optimize metrics like the total processing time or the total heat that is generated or the energy that is consumed and so on. Now, this is a classic hybrid systems problem, right? Where you have multiple continuously evolving states and there are discrete transitions between them, and very easily, depending on what kind of differential equations you have and what are the conditions under which state transitions are allowed, this problem becomes undecidable. So one of the solutions, one possible solution is that you discretize this entire space. And of course, in order to accurately capture the system, you'd like to discretize as fine as possible, but then that results in a state space explosion. Whereas if you discretize in a very coarse manner, scheduling problem, but one that occurs in the context of a production systems domain. We are faced, even after so many years of research in algorithms and scheduling, we are faced with a relatively complex problem that we do not quite know how to solve. So with that, I'm going to stop, and I will be happy to take questions on this, and I pass on the floor to the next speaker. Thank you very much.
Thank you. Thank you very much, Samarjit, for this nice viewpoint of what is cyber-physical systems and what is all related to that. So I think then we can hand over directly to Archimedes. Then you can give your statement as an industry guy.
All right, do you guys see the screen? And just to confirm that my
sure,
full
we
screen.
Can see. We can
All
see.
right, good. So you should be seeing my my cover page called Engineering the Digital Twin. So maybe let me just, I'll give really a brief statement, but something that I've noticed is that the community, right? And I'm here talking about the digital twin community, has focused too much on the runtime aspects of the digital twin. That's where it's exciting for many. But I want to make a case today that the engineering side is as important as the runtime. So let's start by a reflection on where we're at today. So we call this the factory of the future, right? And on the left, you see where we're coming from, right? And on the right-hand side is where we're going to, right? So we come from a model of mass production, right? Where, let's say you are the owner of a product, and you are the one deciding what features the product has, and so in a way you are pushing to the market. You are deciding what is on the product, how it looks like, and you push it to the market. Obviously, you want to produce this as as affordably as possible to make the highest profit. So you are looking that your production line, right? It's fixed in a sense that you can produce the same product in high volumes for as long as possible. And that also forces you, because of the limitations of let's say, machines and so on, production systems, to fewer product variants, okay? But now what we're seeing is that with all the technology in place, right, IoT, robotics, you name it, we are seeing that the market is the one pulling products, right? And right now you go to many of the vendors and you see configurators online where you can configure your product to your liking. But now, of course, the combination space is very large. So effectively what users are starting to do now is creating one-of-a-kind products, right? And now the question is, as a product owner, how do I create a flexible production line? One that lets me combine all these advances in technology, but also that it's adaptive to different product needs, right? So this is what we call lot size one production, the production of one-of-a-kind products, right? At any given point in time. You don't know what the customers will order tonight or tomorrow. So you cannot make assumptions on how to, let's say, hard code and hardwire your machines as you did before. So let's also go, I made a statement that the engineering is as important as the runtime. And there have been some kind of studies, right? All of them informal. There are no hard numbers on this. but I try to compare the cost of engineering, right, relative to the entire cost of ownership for automation. And the model changes, right? In the mass production, what you have on the left-hand side, yes, you want your production line to stay valid for as long as possible, let's say 20, 30 years. But then before, right, with mass production, you invested heavily on engineering upfront, and then your costs of engineering kind of were not there anymore because there were only little tweaks, right, that you had to do, optimization, maintenance, and stuff like that. But with lot size 1 production on the right-hand side, the story changes, right? Yes, you need that upfront investment of engineering, but as you perhaps start producing even different products a year later from when you deployed your production line, you still need to re-engineer continuously, right? So that cost of engineering is not going away as it did before. But also more importantly, right, either left or right, it is estimated that about 50% of the total cost of automation lies in engineering. So then the question is, why are we focusing too much on the runtime aspects, right? We hear about digital twin, like sensors and feeding back all that good stuff to design and optimization, but engineering is as important as the product itself, as the runtime. So just to illustrate this, right, we have this, I want to also highlight that we typically think of digital twins from the product point of view. Think of it like a watch. Yes, we can digitally create and test products. And we only think of that product, in this case, the watch, once it's being used, right? You have the runners, millions of devices streaming data back to, you know, the mothership, and you're doing the analysis. How can we improve the features? How can we optimize it? And that's all okay, right? Obviously, that's one of the benefits of the digital twin. But I think where really the power of digital twin gets unleashed is also that we can digitally model and create these production systems and see, obviously, all that monitoring on the machines themselves that are producing that product. So you see, I guess we like to see it as this horizontal axis where you have the product and the production digital twin that, in a way, intersects the product, right? And only when they intersect is when the production creates that digital product. And I think the important thing here is that the same loops that we see in product, right, on optimization and improvement, so on, we can see them in production. But more importantly, and this is the point, one of the points that I want to make, is that the interplay of the two is something that you don't see very often discussed, right? So the choices that you make, especially if you're creating one-of-a-kind products, the production machine needs extreme flexibility and adaptation, and we need to engineer all that stuff, right? So just a glimpse of where we're at today, and this is a little bit to talk about the problems, right? I just put pictures of many of our tools that let us create both product and production digital twins. Now, obviously, there are integrations between them, right? But we are working, and also this is the challenge, not only for Siemens, but for everybody else, and also Siemens and other companies, to start creating more interoperable digital twin creation tools. So here, what you see on the screen is all engineering. We're creating stuff. We're preparing both the product and the production. But as we discussed before, the cost of engineering is very high. So what we're doing, or we've been doing this for, I don't know, the last 2 years, is something that we call cognitive engineering, right? And here the idea is the use of AI, right, or artificial intelligence, and here not only machine learning, but also formal methods and other forms of AI. The goal is to reduce the engineering effort. It is costly, it is difficult, and we want to address that. So what we've come up with are proof of concepts, and this is just one of them. We call this the Ardu Code, right? And the idea here, what you see in the middle, is this proof of concept that we created is attached to our tools on the left. That's for PLC programming, and on the right for production scheduling and simulation, production planning. And here, the cognitive engineering system, or the one in the middle, is constantly monitoring, right, different projects that we've created in the past and picking up patterns, right? All driven by a knowledge graph or a knowledge base. And what we're trying to do here, and we've demonstrated that it can be done, code classification, try to reuse code based on functionality. Number two, semantic code search recommendations. If you see a hardware pattern being implemented, you can associate this piece of code that controls it. And third, the hardware configuration. For example, the use case that we have is that if because of the structures you detect that this requires a higher safety level, you can recommend an additional PLC to cope with that requirement. Also, very importantly in engineering is that we have an aging workforce, right? That happens all the time. We're humans, we only last, I don't know, if we're lucky, 80 years, right? But then as our engineers retire, we need to train the new generation. So capturing that engineering knowledge is critical, right? And that's what makes the difference between an experienced, very proficient engineer and someone that you just hire from university or, from school. So here, what we've been studying too is that as engineers create structures in the tools, in the engineering tools, we can mine these structures to try to predict what makes the engineer senior engineer more efficient and, let's say, more knowledgeable than other, and capture this pattern so that we can recommend them later to newcomers. So with that, I'll close up, and I want to just emphasize three key takeaways, in my opinion, right? This is what I want to discuss. One, that engineering accounts for about 50% of the total cost of automation. So it's as equally important as the runtime. So please, number two, pay more attention to engineering. And three, as you pay attention to product digital twins, start paying attention to production digital twins. So thank you for listening in, and looking forward to the discussion.
Thank you, Aki, for also this very nice perspective how you do in industry. And now finally we go to the next panelist, to Franco Fumi, and he worked also in this digital twin area with production system. We have also a short lab visit, but I will not say so much because Franco, this is your turn. So then you can already start.
Okay, thank you, Achim. So my presentation is about a research facility for Industry 4.0, where in the core there is digital twins, as you will see in a demo that we will do at the end, a live demo that we will do at the end of my presentation. What can we say about the flow that produced the digital twins that I will show you? That if you consider production trends and needs, we can see that the current production trend and needs are sensibly different from the ones of 10, 20, 30, 40, 50 years ago. Particularly, we can consider that all the goods which are now produced in small personalized batches. No longer there are large unpersonalized batches. And so it is fundamental to create a correct monitoring of the production. And this could be enabled by using digital shadow, which is a particular kind of digital twin. And particularly in the case you are able to reconfigure dynamically the production. This dynamic reconfiguration goes in the direction to have predictive analysis of plant reconfiguration, which is a topic which is on the border between Industry 4.0 and what it is already called Industry 5.0. But first of all, let me say something about what we succeeded to put together into our research facility. We started from all the typical enabling technology of Industry 4.0. We realized that all the technologies are based on computer engineering, but computer engineer is not exactly what there is in the core of the majority of the production plant. We can find there a lot of different engineers, mechanical engineers, control engineers, electronic engineers, but not a lot of computer engineers. And particularly all the methodologies which has been used in computer engineering in the past decades for designing software, for designing system, must be applied in the context of industrial computer engineering. So the target and the goal, the mission of the laboratory that we created is exactly to try to identify a way to port all such methodologies and knowledge into industrial computer engineering. We succeeded to do it only because we receive a huge funding from our education, university and research ministry, 8 million funding, and this has been used for some activities, but also to create a laboratory. The laboratory is called ICE, Industrial Computer Engineering. Okay, here there is the website if you are more interested about the content. And the goal is to create a completely reconfigurable production line, be careful, able to interact with humans. this is the new frontier, interactive humans of Industry 5.0. It is exactly what we are going to do in the next years after the first stabilization of the production line that will implement all the main characteristics of Industry 4.0. And the interesting thing of ICE is that it is a so-called demonstration lab. So what is a demonstration lab and why it could be a bridge between academia and industry? Because a demonstration lab shows the state of the practice, okay? And the state of the practice must be there. But then on top of the state of the practice, we are doing teaching, so we are doing specialized teaching. We are doing research. It is fundamental to make research if you start from the state of the practice. And it is extremely comfortable to interact with companies. In fact, when there is a company that arrives by us to perform the chronology transfer, the company perfectly consider what we are showing something that is very close to its business. We received 32 companies in the past 1 year and 1.5, even under this pandemic situation. And you can see also numbers related to contracts that we succeeded to obtain by interacting with companies. So it is a real need of companies to identify an intermediate position, intermediate situation between the direct offer of companies like Siemens, for sure, and the ideas of universities, because the ones are focalized to the target project and so on, and they are perfect for sure, but focalized to one direction. The ones of the universities are, in the majority of cases, the proof of concepts. So we need to identify an intermediate point. This laboratory tried to identify this intermediate point. First of all, it is not completely built from scratch. It was not possible. We started 2 years ago, but we succeeded to arrive to the situation in which we are, and you will see in the demo, only because it is a patchwork on industrial contribution. By the way, we have a strong relationship with Siemens, so all the software of Siemens are used and implemented into the laboratory and then are extended with our research and with our ideas. The shape of the laboratory is this one. You can see numbers from 1 to 8, which represent the hardware part of the laboratory. We implemented an hardware part because we realize as computer engineer that in this field, it is necessary to have hardware. It is not so easy to identify models which could be simulated only partial. So if you want to be credible with respect to companies, you need to show real machineries. And in fact, we have vertical storage, we have mobile robots, an area for geometric quality control, an area for assembling with the collaborative robots of different brands working together, another for 3D printing, another for subtractive printing, another for electronic functional testing, and then there is the transportation line made by using mini pallets. On top of this hardware, there are all the software layers from 9 to 17. All such layers implement something which is in the state of the practice. So, for example, all the tools that we bought from the EDA companies and some other software that we implemented, which represent the state of the art and which represent the level of researches. One interesting extension could be, for example, the one related to edge cloud computing. Let me make you an example. There are mobile robots here which move all around the laboratory, and the complex software of these mobile robots move dynamically from the local side, the local PC on top of the robot, into the cloud and vice versa. Or, for instance, the data collection architecture is a collection of software, cloud native software, which allows to move data from the edge to the cloud in a very smooth way. But to represent the complexity of the laboratory, we can consider this that we call the roadmap to Industry 4.0. This is what we propose to any company that came to us to visit us. And we say, okay, if you like to arrive to implement all the direction of Industry 4.0, you have to go through this path. Perhaps we have already at one of the levels of this path, but otherwise you have to start. You need, for example, a model of your line. We are using SysML as typical language for modeling to represent the system. You have to have a way to extract data from the production line. So you need to interact with sensors or use specific protocols like OPC way. You have to have a data collection architecture to collect data. And then if you start from this condition in which data are collected, you can also start to think to a digital twin. There is no sense to think before if you don't have the starting lines, the starting points. If you would like to start with a digital twin, our advice is start with a digital shadow. That is a digital twin that do not require specific complex models, but which go on in the simulation by using real data. This is a way to monitor what's happened, and by using real data, you can accumulate real data, and then from the data, you can also derive models. And so you can also extend in the future your digital shadow to become a digital twin. Then for sure, you have to present data and to perform analytics on top of them. If you like to put all together, so you arrive to have our industrial computer engineering lab. So only 3 very fast slides about the technicians. Okay, this is a methodology that we implemented to generate the global model of the laboratory by collecting what there is already in a company. If you enter in a company, you cannot say, okay, stay calm, now we will generate the model of your factory, we will go away and we come back in 2 years with the model of 2 factories. There is no sense. We have to start with what there is already there. And for example, models like business process model and notations are usually already available into medium, large companies, or models like automation ML has been used by the producers of the different machineries, or ISA 95, a typical standard for manufacturing execution system. We are able to collect all such information and to arrive to a SysML model. From this, we can start to automatically or semi-automatically generate the pieces of the roadmap that I showed you before. So for example, in the case of data extraction, you have to solve the problem of different protocols. You have to mix together IoT, what we know IoT, with industrial IoT, which is a different flavor of IoT, more related to industrial production. You need, for sure, for example, a gateway. But if you don't become crazy, you need an automatic way to generate the data structure in order to collect data, in order to arrive to have an architecture that eventually should be cloud native, in order to be able to move it from your PC to an industrial PC, to a large PC, to a cloud, without being constrained to redesign all software. And in the case of data collection architecture, a good idea is to avoid to put all data into the cloud. You can do it, but it costs a lot, it is useless. You have to identify different layers, and in such layers, you have to remove useless data. You have unified the data from different sources, and then when they are ready, you can put them into your favorite cloud. And then on top of this, you can describe, you can model your digital shadow. We are using, for example, the typical simulator of Siemens to perform this. We extended them by mixing them at the different levels in order to have different digital twins. Because sometimes we use the term, let we generate a digital twin, but there is not only one digital twin. There is one digital twin for each problem. So depending on the problem that you have to solve, you need to identify the correct level of abstraction, you need to identify the correct set of data, you need to identify the correct computational model, and so on, in order to identify what exactly you would like to simulate. At the end, you have to collect all data to present them with some analytics tools. And with this slide, which resummarizes the laboratory, I would like to pass the word, the token, to my colleague in ICE Lab in order to show directly a live demo of what we have.
Hi all, and welcome to the ICE Laboratory in this digital presentation of the lab. Before I show you
the... You might want to stop the screen sharing, then...
Yes. Franco, can you stop your screen? This is right, some of the things. Because then we have to...
Okay, okay. Do you see me?
Yes,
okay.
Now it's better, yeah.
Okay, welcome again to the ICE Laboratory. And before I show you the digital twin of the lab, I show you the real brief show of the real lab. Okay, we have the lab divided into working cells. The first one is the Ferretto warehouse that we use to store our production pieces and the the piece we need to do our working in the laboratory. Then we have the transportation line, which is a mini pallet line in conjunction with a smart mobile robot. Then we have an optical quality control, which is made by cameras and a powerful PC. The robotic assembly and disassembly station, which is working now, doing our recipes. And then the 3D printers, we have 2 of them with different technology. The subtractive manufacturing station, which is a milling machine in conjunction with where robots. We are working to integrate that in the laboratory. And then the future part of the laboratory, the flying probe tester to test and do automatic core testing with something which will we do in the future. I show you the digital twin with a screen sharing. Okay, you should see on your screen our digital twin. The digital twin show up the data flowing from the production line. For example, on the warehouse, you see the current tray that is on the bay. From the optical quality control, we see the last event, which is a correct quality control. From the robot, now you see an empty cells, but when the robot places the Lego pieces in their buffer area, you can see the state of the cell, and then finally you can see the mini pallet flowing on the line in their upper state and in their position. Our digital twin reacts to changes on the line. For example, I can show you, if Marco is going, that if I stop this mini pallet on the digital twin, there will be a waiting, and the pallet at the end of the line doesn't come up. Then, when I leave the pallet, the digital twin shows exactly the pallet flowing on the line. But also, if I extract the pallet from the line and put it in another point, you will see that the digital twin will show up a blue pallet, and then at the first time the pallet reaches an RFID sensor, the digital twin recognizes it and insert it again in the line with its contents on top. Few moments. Okay, you can see in the digital twin that the pallet switch from blue to the normal state. This is possible because all the machines we have in the lab have OPC1 server from which we can collect the data, and we can use it for controlling the plant. Also, then the data collected from the machine flows in our data collection architecture, which we use to store the data. Can I reduce?
The zoom bar is over the tabs.
I have a problem with the zoom bar. Yeah.
No worries.
Let me extend. Okay. So here we can collect the data and show you some of them. Here is a dashboard showing the actual power used from the ICE laboratory and from each of our controlled machine, connected machine. Then I can show you another dashboard where we mix the data from the environment and from the plant. For example, we are showing the data of the ambient, where we are showing looks, the illumination of the laboratory, the temperature of the laboratory, and its humidity. At the end of the production line, at the start of the production line. Then we can show in real time the consumption of the pallet line, the quality control, and the two robots. And this is the state of the ambient lighting. So we are using 100% of the lighting power of the laboratory. Downstairs, we are showing information from the past activity of the lab. For example, how many times each type of Duplo has been recognized by the visual control system, how many quality control has been performed, how many correct pieces has been processed, and how many fault pieces we had in our production. Of course, we have other data. For example, about the warehouse, we store how many times each tray has been called, and in this area, how many times each robot has been called in our recipes. And finally, we have some counters about the state of each element in the conveyor. We show only a few of them. For example, how many times we switch a piece that lock the pallets on the conveyor, how many times the belt of each bay has been moved, and how many times the motor has been on for each belt we have on the production line. We store all this data on this database, which is InfluxDB, and is fully optimized to store time series data. We are collecting a wide range of data, and here you can see raw data about our buildings, the temperature of ice lab and of the room near the laboratory, and its humidity. In this case, is the other lab we have here in this building. Finally, we have a cloud part of this architecture. In fact, not all the data, we cannot push on the cloud all the data, but we do some pre-processing. For example, you can see from the previous dashboard that we have 2 points where we measure temperature in ice lab. Before pushing this data online on Siemens MindSphere to let them available to a wide range of customers, for example, for us, our students, we do a mean between them, and we show only one line of data, which is undersampled than the original time series. I think I show you.
Hey, Carlo, thank you very much for the show. I think you gave a good idea of what we have in the laboratory.
I close the. So again,
thank you,
Franco, the screen.
Okay, thank you very much also for this nice view in your lab, Franco, and also your colleague who presented everything inside the lab. That was really, really nice, and also good to see that this is working. Yeah? It's not only, let's say, it's not only some kind of concept, digital twin. You can see this really working. So now we have the panel, and I would like to ask the audience to use also the Q&A. You have on your Zoom, and down on the right side there's a Q&A. You can ask questions, and then you can write down your questions. And in the meanwhile, we can start also with some discussions here from the two moderators to the panelists. So then I would like to start also like a little bit like in order of the talk. I will start with Samarjit. You're already smiling. And my question in this case, because you said we have to handle this in increasing complexity, but I think this complexity is growing tremendously. Also, we have this multi-criticality. I think, can we handle that all with models? I mean, models, you know what Edward Lee is saying, model is not everything. We have this nice book, Plato and the narrative explained also a little bit there about this modeling. Can you say something about that? I mean, how we can handle that in real?
Right. Yeah, you are absolutely right. As the system is growing in complexity, there is also a big modeling complexity. So traditionally, one way of handling this problem was, so to speak, the separation of concerns, right? And which is also what I tried to say at the very beginning, that the traditional design flow has been that you model the plant and you design the controller, but the control theories does not take into account the details of an implementation platform. And this is also the usual practice in the industry, that there is a completely different group that then takes into account the design of the platform and the configuration of the platform. And then there is a third group who then takes these pre-designed components and tries to put them together. But given the pressures of optimizing things and getting efficiency and reducing time to market and so on, as I think increasingly we are seeing that this separation of concerns does not quite work. And there has been a lot of talk on cross-layer design, where you then integrate multiple models and optimized across different layers of models. So I kind of feel that we are probably moving more into this direction of, instead of separately modeling different things, how do we come up with interactions between these models? And which is also something that people like Edward Lee with Ptolemy and also now are trying to promote, that can we have models that can really be coupled with each other, and can we have executable models? But I think overall, this is a big challenge. Also, I think this provides quite a bit of food for thought for us in academia to try to see how do we integrate these different models as well as cope with this complexity.
That is true. Yeah, I can fully agree with you. I mean, it's also a problem if we have now different models, how we ensure that they are consistent to each other. That's another topic. Yeah?
Absolutely, absolutely. And I think, again, there are different techniques available in the domain of formal verification. And I think, as for example, also we saw in that demo, right, that even in an industrial production system, there are really different groups working on different parts. And I also try to highlight this problem of consistency. And maybe at the end of the day, everybody is committing their developments or changes into a cloud. And then overnight, there is a consistency management unit that runs and checks for consistency. And next day, when you come back, you see these are probably the inconsistencies that you need to fix. So I think all of this complexities, on one hand, difficult to handle, but also for us in academia, they also pose very interesting problems.
Okay, thank you, Simon.
If I can say something about the consistency, we have had the same problems by starting from the aggregation of different information. Because I mentioned it before, SysML has a way to represent all the characteristics of the cyber physical production systems.
Right.
But if you arrive to such a model starting from a description, which has been already did by other groups of research, other groups of implementation, and so on, then when you have a global description, you need to verify the consistency. And what we did, for example, is to use the theory of assumed guarantee contracts. This is a theory which has been already passed from the research into the practice, and it is a good framework to represent what each component assumes with respect to the surrounding components and what the component can guarantee to the others. But the level, the complexity of this could be balanced by using different logics. So depending on the logics, that you put into the assumed guarantee contracts, you can obtain more or less problems to be checked. So you can then spam from model checking to simulation to whatever you like, depending on the level of security that you would like to have. So I think it's fundamental to aggregate together information which has been pre-designed. Also because it is very strange to enter in a company and to find a production line that must be built from scratch. This would be fantastic, but usually you have to take care of what there is already implemented, and you have to reuse what there are.
Thanks, Franco. There is also a question from the audience. Baham Javadi kindly ask the panelists their view on how important is the role of edge cloud ecosystem. What is the trend in the research and industry? So maybe we can start.
I can answer.
Or Franco?
Yeah, sure.
Okay, go on, Archimedes.
Yeah, no, I guess, look, I think edge cloud is not something that I'm very familiar with. I mean, I do understand it, but I think obviously the edge piece is critical for monitoring, right? The real-time monitoring of the production system and the product. But I think also the interesting thing about the cloud, and also probably this has been discussed, you know, everywhere and so many times, but I guess one of the challenges there is the data privacy concerns, and maybe privacy is not the right word, but how do we secure the data, right? There are cases, I don't know, let's say for some technologies that have export control, how do you deal with that segmentation of how you call it, the access control, right? And to make sure that those cloud platforms actually honor that, and all the safety mechanisms and security mechanisms to protect that and to guarantee that export controls are honored and so on. So I guess just pointing out some of the probably obvious, but some of the ones, the problems that keep us awake at night.
If I can report my experience, that is the partitioning of component software between edge and cloud has been always a nightmare. A nightmare because you have to define in advance which is this partitioning, and then when you create software for the edge and then software for the cloud, such software cannot be easily moved from one level to the other. But since not many years, there is an interesting technology which can be called cloud native, which is based on some software like Kubernetes, which is now available from small pieces of hardware like sensors, more or less, up to edge computing, up to cloud. And since you have the same infrastructure, which is common to all such different levels of architecture and level of computation, you can, if you prepare your software to be cloud native, you can simply move software from one condition to another, from the edge to cloud and vice versa. And this is fantastic, particularly in the case you are able, but this is moving from the state of the practice to the state of the art. This is moving automatically depending on the computational resources that you have. At the moment, you have to perform a static allocation, but again, you can move them, you can move the piece of software without being constrained to rebuild them and to recompile, resynthesize, and so on. So this is a good news for having an architecture which is a continuous from the edge to the cloud.
Thank you, Franco. There is another question for you that talked about contracts. Stefan Henkler asked, how do you get the contracts on the right abstraction level when dealing with different models?
This is a very good question, because when you use the term contracts, there is not only one way to write contracts, but there is an infinite way to write contracts. So the problem again is the level of verification that you would like to do. If you would like to verify the correct integration, you can derive the structure of the contracts from the CSML model, but you cannot derive the internal part of the contracts. So there is still a manual activity that should be to coding contracts with respect to the specific problem that you would like to check. But the structure of the contracts could be automatically generated by the interfaces of the different components. And for example, I'm still talking about SysML, but also there are some other modeling languages. You have a lot of information to reuse them to generate the skeleton. Then another point is that a contract must be based on some primitive activities, primitive actions. Which are the primitive actions? This depends again on the selection that you would like to do. At which level do you want to stop the subdivision of contracts and the specialization of contracts? For example, with respect to typical machineries of an industrial production plant, you can find taxonomies, which you can find in the literature, and you can extract primitive activities from such a taxonomies. In some other cases, you have not a taxonomy already did, so you need to model your own set of primitive activities to be used as a starting component for the contracts. So from the top, you can generate the skeleton. From the bottom, from the taxonomy, you can identify the different activities, and then the connection, the moment in my knowledge, must be written by hands.
So maybe can I add one thing about this thing of contracts, right? I just also want to point out one example on how engineering is so brittle, right? We deal a lot, and probably I'm just guessing, right? But based on what I saw, Franco, a lot of your SysML descriptions are to ensure that the machines actually produce, right? But you see, the example that I have, you tell me whether that's the case or not, but you showed a very nice dashboard, web-based dashboard, where you had your conveyor belt arranged in the exact way the production system is configured. Now, if for any reason, a month later, you make a change in the topology of your conveyor belt, maybe your SysML model will ensure that it still adapts to that change. But then your web view of the conveyor belt, someone needs to go and do the change. That means write some JavaScript, some whatever technology you use for that visualization. So you see, again, it's another example where engineering is always an afterthought, but it's as important as the runtime, because ideally you would want that whenever there is a topological change, you see that reflected also not only in your production model, but everything, all the stuff that deals with that notion of a conveyor belt gets updated, right? Without no one intervening manually, right?
You are perfectly right. So now I'm moving from the state of the art to the state of the practice to the state of the art. That is, we have a methodology to automatically generate from SysML all the different components. So all the interfaces of the data collection architecture, or the OPC-UA servers and clients, all the different pieces. But this is the current research that we are doing. But in any case, if you have a model expressive enough, like SysML with all the other stuff, you, in theory, could push a button and obtain all the software which will be deployed on the different levels of your architecture. I think this is correct to do. That is correct by construction if the model is correct. And I don't know fastest way to do this.
Yeah, got it.
But I think I think, as Franco said, right, that they are synthesizing these things from the SysML specification. But as we all know, right, that synthesis in general is a very difficult problem, right? Even for relatively simple cases, even verification, that is, everything is given and you are trying to check whether a certain property is being satisfied or not. Even verification is a difficult problem, and synthesis is more difficult than verification, because there you are given the property and you are trying to synthesize something to meet that property. So I think there is probably a lot of scope in this direction, right, to try to break down the problem into simpler parts and synthesize the simpler parts and then compose things together. In computer science, we know a lot about compositional modeling and composition and so on, which is like the fundamental bedrock of computer science. So there, I think, for this kind of complex systems, and I think industrial production systems, and with all the industry 4.0 and our vision of how things should work, I think there is a big scope in trying to develop new synthesis techniques, trying to develop new compositional techniques, and address exactly the kind of problems that you mentioned, that, you know, in a flexible manufacturing system, if the production line changes, then how do I also subsequently generate the web scripts and JavaScripts and so on to change the view.
Okay, I think there was one more question we could do, no, Graziano? There was one more question from, you can do it, you can say.
Yeah, there is one question from Donatus Emeka. Let's say, how do I be part of this project? I don't know if he's thinking or she's thinking about the Francos project, probably. And another question is by Charles Steinmetz. Do you think we need defined standard or guideline for creating digital twins, something like design pattern or best practices for software development? Or creating digital twins is something really flexible and varies based on each use case? Difficult question.
Yeah.
I think the project is so interesting that everybody would be interested in joining Franco's project.
Yes, true.
We are available to cooperate with any person interested too, because it is an infrastructure. So on top of the infrastructure, it should be easy for any group to create their own level of software to verify, to check. What I can say about the question, yes, there are already some standards also for cooperating. Let me mention one very famous standard for creating digital twins, which is the FMI-FMU interface, functional mockup interface, functional mockup unit, which has been built in the past 10 years in the automotive area to connect together simulator coming from different field. The main idea of this standard is to create a wrapper of your model, and into the wrapper you can also put the simulator in one of the possible cases of the different level of the standard, and then you have a component and you can connect this component to another one, which is another simulator with another model with, for example, a completely different area of your project. The standard is very good. The only problem is that the standard assumes that there is the same computational model for all the FMUs. This is not so easy. Usually each FMU has its own computational model, and when you put all the pieces together, it's not so easy that all works. But in theory, this could be a good standard. There is also another standard, not remember the name, related to the collection of digital twins on top of a shared infrastructure. Something like the GitHub, for example, for software, but directed to digital twin. But I don't know exactly the maturity of the standard, while the FMI-FMU is very mature.
Okay, so we're running already out of the end of our panel session because it's only 15 minutes after. So then I would like to thank again all the panelists. I think you could see, I mean, we could talk hours about this topic, I'm pretty sure. And I mean, people who are interested, I mean, you can also send probably emails to all the panelists for sure. And I think they will also happy to answer. And also if you have questions to Graziano and me, you can also send emails for sure. So then I will hand over again, last but not least, to the organizer, to Christina. She wants to say at the end finally some words about how this video will be handled so that everybody is aware where all this data goes. So Christina, question is up to you.
So first of all, thank you very much again to our panelists and to our organizers for putting together this panel. It has been very interesting and entertaining, I think, for everybody. And for everybody who is interested, I mentioned at the beginning that this was the second out of 10 panels in our Future of Information Processing event series. I just posted a link in the chat where you will find more information on these events and also on the Jubilee of IFIP, which is turning 60 this year. Thank you very much again, and I hope to see you in a few weeks at our next event or other activities online. Thank you very much.